All right. Again, good morning. Sorry for being late a little bit today, but we will be talking about heat waves, urban island, heat island, and landslides today. On day one, we talked about climate change basics or general terms, and then day two, floods. Yesterday, drought. Again, we are kind of touching the broad topics, not getting into the details, but at least it gives you some exposure. But again, I have, like I said before, I have lots of articles to give you with the bundle that you will have with all the files and the papers. You can download, read them through, but any other follow-up discussions that you want to have, we can have it later by email also. For this also, I have plenty of articles to share with you. I have extracted, this is not my directly related research, but the topic is itself, important, especially for India. So I have tried my best to collect articles from different sources, the case studies, news reports, varieties of sources that I have done, and I have also given you the link for you to go and explore yourselves. Okay, and please bear with me. I kind of want to touch on some of the basics, and those who are not directly related to the topic of hydrometeorology might find it little difficult, but I'm sure I can break it down in a way that you can follow, at least to get a big picture view of things. It's important that way, you will at least know when you are doing the modeling, or when you try to understand the extreme events, you will at least have some scientific you know flavor of stimulating your thoughts. Just to stimulate your thoughts, I'm going to introduce you to some of those concepts or hardcore things about land atmospheric interaction and urban heat island effects and all that. We have 2 hours lecture today for this topic, but I will space it out in a way that we will finish 50% of it before the first break at 10:15, and then have a coffee break, tea break, and then come back and finish the remaining part. Landslides, I will show Wayanad as well as Chamoli, the place that I visited to look at this, but we will start with the heat wave because that's a bigger circulation related process that we need to understand. I want to touch this particular water cycle program or schematic that I mentioned this before also. These are ideally the interlink between land and atmosphere, right? In the water cycle analysis, people have used this for 100 plus years. But again, you can refer to this paper. This is extracted from this, but that graphic is very useful for you to know where we have modified this partitioning of this water budget with multiple things here. In this particular graphic, I'm sorry, you may not be able to see the details, but the intent here is to show that we have modified the landscape, and then we have particularly modified how we use the water, and that changes the whole dynamics of ET or evapotranspiration, precipitation, and then the runoff partitioning on the ground. There are three waters that we talk about here when you look at it closely. One is called green water, the other one is called blue water, the third one is gray water. The basics of that is basically, when you talk about green water, anything that comes as rainfall stored in the soil, used for crops or, for us in some form, they are called as green water. Blue water is the one, is the consumptive use, basically for irrigation or industrial commercial use that we take water from river, reservoirs and all that. That will come under blue water. Gray water is the one that we deal with when we talk about industrial pollutants, recycling them, reusing them, and that is another component of water we still use in some places. Yesterday you saw in the video, the speaker was presenting about how to recycle and use it for irrigation. When you recycle and use the wastewater into other applications, that's a gray water concept. So we have included those in the water cycle. Now we are adding water from groundwater to other, sources of water, to our day-to-day applications. So it adds more water on the landmass. So that means it could be leading to more evapotranspiration, or it could, depending on the location, it can also be reduced evaporation if you don't want to apply that water. So essentially, the supply and demand that we see from the natural system is modified. That's the message you need to be taking out from this graphic. And if you read this paper, it talks about how we have changed, but we have not changed in our thinking to represent the reality of this water cycle in our calculations, in our models, and things like that. But of course, that's the part that people are now doing in models. I should take that back, because people are dealing with adding all these components in the model, including my own research group. We do that. Now, let's talk about extreme heat. That is related, yeah, because the reason is water cycle is very important in the way how much moisture you have on the ground, how much is the precipitation source and all that. Just pay attention to this graphic. This is little bit of dated 2016 or so, but again and again, I think that's what we are seeing here. The gray shaded area is the total global land, and of course the land surface area divided by the grid points from the models that they have used or calculated, and of course it closely represents the global land mass. Okay, and then when we look at the number of warm months, warm events in 2016, for example, particularly India, you see 4, 5, 6 months of extreme or warmer months. When we talk about extreme, you remember we talked about extreme events, anything deviating from the long-term average of between 4.5 to 6 degree Celsius in the first day that we talked about on the extreme events. Kind of that classification they have done here and identified these heat waves for Asia. That's what you are seeing here in the red line, is really spiking regularly. 1998 or 2010, 2016, even in the last 10 years, if you see many times of heat wave, from March through May or June, you all have witnessed these heat waves, right? Unbearable heat, and we try to really adjust to that, or come to the AC room or avoid direct sun and things like that. Why is it happening? Right? That's the question that we want to be understanding. For that, I have to start from some of the atmospheric science concepts. I'm not an atmospheric scientist, but at least I just want to introduce the concept of the stability and hydrostatics and all that. So you may have seen this equation from before, change in temperature over elevation, right? Simple concept. When you go up, the temperature should go down. It's cooling, right? It's the cooling part. That's based on this, what we call as the rising of air mass or sinking of air mass when it happens with no exchange of heat. That's called dry adiabatic lapse rate, DALR. Um, then the parcel itself either will lose the heat or gain the heat. That's what the process is. When, let's say, you send the balloon up, it changes the temperature based on the elevation, right? So assume like that air parcel, air pockets that moves into the atmosphere. So that parcel will lose the temperature when it goes up because of this relationship, gravity over specific heat capacity of air. It's about 9.8 Kelvin per kilometer drop in temperature that we have, right? As you go up by every kilometer in the sky, 1,000 meter, 2,000, 3,000, at the altitude of the flights, which is about 10 kilometers, let's say, we are talking about, you know, at least a significant drop, 10 times of 9.8 Kelvin drop in temperature. Sometimes I've seen minus 55 C outside of the air, and you may have also seen that. That's because dT over dZ is equal to minus 9.81 divided by the specific heat capacity of air comes out to be 9.8 Kelvin per kilometer. That's what is happening when the air parcel is going. Okay, so keep that idea in your mind. And when I'm talking about stability, atmospheric stability, This concept applies here. So people have come up with that relationship, and then this is the relationship. As the temperature, as the elevation goes up, the temperature drops, right? So basically, this is the solid line is your lapse rate, ideal lapse rate. But when the air parcel from the ground, because of daytime heating or something else happens, urban area, right? So that air parcel goes up and it loses the temperature. And if the temperature loss is greater than this triadiabatic lapse rate, on the other side, this parcel is going up like this, right? The atmosphere becomes unstable. So the warmer air mass surrounded by colder air, there is no exchange between them, but it creates that kind of a turbulence and mixing and confusion, chaos in the atmosphere. That's unstable atmosphere. Okay? The opposite is the case for the same air parcel that's losing the temperature with as the elevation goes up, as smaller the dot, the dotted or dashed line that what we see, than the dry adiabatic lapse rate. Then atmosphere is not destabilized. It is not unstable. It is stable. Why are we talking about this? This confusion in the atmosphere is the reason why we get rainfall, thunderstorms, heat wave produced air parcel that's going up and cooling the surface back again as precipitation. All of those connections that we can establish. That is based on this TALR and the air parcel that's going up and down based on the temperature conditions. So I think the same thing what I'm repeating here in terms of words, you will see. Unstable conditions are due to daytime heating. Think like that. Because of the sun in the morning when it comes up, it heats the ground. It makes the air lighter, warmer. It goes up in the afternoon, late afternoon, in the evening, creates these thunderstorms, convective precipitation, right? But in the night time, that is not the case. Atmosphere is more or less stable because the air's, the land mass, air pockets near the land mass is not that warm. It's, the pocket of air that goes up will not be really losing the, or keeping the temperature in the unstable condition. The stable condition is the opposite. As they go up, because of the ground cooling, if there is a warm layer comes on the top, still we call this as an inversion case, right? When you go up, the temperature cools down, right? But in the other case, in the stable atmospheric case, what happens is because of winter time or cold air front coming and occupying, let's say, first 100, 200, 500 meters of the ground surface, and there is an air mass above that coming, it will not still mix up. It's going to keep the um, mixing very minimal. So the atmosphere is kind of stable in that case. So it is also cool. The nighttime calm, sunny day conditions, this is what happens. And this is ideally the case for even pollution. When there is no mixing that happens, when we emanate or when we release all these pollutions, pollutants, particles, that aerosols and things like that, they don't leave the surface and it doesn't get mixed up and it doesn't get carried away because of calm winds and all that. Delhi is the example that we can think of, that kind of a condition. Atmosphere is stable, Himalayan block is there, there is no mixing that's happening in the atmospheric columns, the air that is trapped with aerosols creating all these smog conditions. And that's a stable atmosphere, but that happens. This is very important for us to understand the regional dynamics. I'll come back to another concept also here. There is a ratio called Bowen ratio, ratio of sensible over latent heat flux. You've seen this diagram before. I'm repeating this. The reason is sun is our source of energy, right? We partition them into outgoing long short wave, incoming long short wave, radiation, how much is absorbed on the ground. We have seen that before. Just keep that in mind. This ratio is the ratio of heating up the air as sensible heat flux. When you really say that it's a warm day, you're talking about sensible heat flux being higher. Think like that. And when the plants actually have enough moisture and when they transpire as evapotranspiration, that is the term for latent heat flux in energy units, watts per square meter. So we divide sensible over latent heat flux to get the Bowen ratio. There are instruments available to measure this. So assume that we are going to have a ratio. Now we will come to this side here, bare soil. Under bare soil conditions, there is no moisture or vegetation that takes the heat from the sun. So that actually comes out of the soil, reflects from the soil, and then it heats the air. That's why we feel hot, that on a hot, dry day in a bare soil relative to a vegetated soil or a irrigated soil. So when the turbulent heat flux is high, of course, your Bowen ratio is going to be high, right? It's really significantly high under dry soil conditions. The opposite is the case with respect to wet soil conditions. Bowen ratio is zero or nearly very small. So this concept is also important. Bowen ratio is the energy that we split as a ratio between sensible over latent heat flux. Think about the atmospheric conditions, stable, unstable conditions, and vegetated versus bare soil conditions. One more thing, extension of that same concept here is the effect of either precipitation or artificial moisture that we add as irrigation. There are three conditions that I'm talking about: dry soil, moderate soil, and wet soil. What happens under dry soil conditions, meaning when there is not much moisture? Yesterday or day before yesterday, we had plenty of rain. You saw even the grass completely soaked with moisture. That is not dry soil that I'm talking about. Bone dry, when there is not enough rainfall or something like that, when you see the dry conditions, assume that is the time, the dry soil is here. Most of the energy that is being spent for heating up the air compared to heating up the plants or vegetation, because there is not much vegetation. So blue is your latent heat flux or evapotranspiration, taken by the plants and released as water vapor. That is going to be very less compared to sensible heat flux under dry soil conditions. Opposite is the case with the wet soil conditions. Less sensible heat flux because most of the energy is used by plants and the soil for transpiring as latent heat flux. So that's why you have more latent heat flux under wet soil conditions. Moderately wet conditions, you have equal mix of latent heat flux and sensible heat flux. So the solar radiation is being partitioned into latent, sensible, and ground heat flux is the part that I did not talk about. Some part of the heat is getting into the ground, going into the soil, deep soil, stays there for a long time. So this dynamic is very important. When you apply water, transpires as ET, increases humidity near the surface. You feel muggy, you feel humid, your skin sticks when you go out. That's the condition for humidity, increased humidity when the wet soil exists and when there is more evapotranspiration happens. And when there is less evapotranspiration under dry soil conditions, of course, you don't see that water vapor going up. You don't see that formed as clouds, right? So the planetary boundary layer thickness is really high under dry conditions compared to the wet soil conditions where your planetary boundary layer thickness can be lower because the evaporation creates clouds and that cloud becomes the PBL thickness. We found out that up to about 1000 to 2000 meter difference between dry and wet conditions of this planetary boundary layer thickness. So that can happen. So what I'm trying to say here is that atmosphere is always dynamic from day to night, and then vegetation plays a role, sun plays a role, and then all of these mixing things happen. So now put this perspective for the heat conditions. Now in the atmosphere, if you look at, this is a textbook example, that's why it's old and I see that as gray color. Just bear with me on this one. Potential temperature is the variable that people, particularly meteorologists, measure. Okay, here, of course, for the height, the contour is here. And then this is for 24 hours. Okay, x-axis is 24 hours with respect to height from ground level to 3000 kilometer. They measure the temperature. You can see because of no radiation or sun, solar radiation, the temperature is not really changing much, but then it starts slowly going up, right? in the middle of the afternoon. So this graph is between 3 a.m. and 3 p.m. This is 3 a.m., 3 p.m. So there are two lines there, right? So 3 p.m., the atmosphere becomes more or less homogeneous with heating. So the temperature, what you see on the ground is more or less the same at 3 kilometer height. Okay. The opposite is the case for moist conditions. So when I'm looking at the wet surface, you are looking at um, temperature more or less the same. The dry soil, of course, converts more heat that we see as nonlinear relationship here, which is not the case here. It's more or less the same. Heating up also very uniform, and the humidity is also more or less the same, unlike here. Dry and wet soil or moist soil behave so differently, right? So that's one thing that we have to think about. And then feedbacks, the cloud feedbacks process. That's very important for us to come to a conclusion on heat waves. This is again the illustration of previously explained concept. This is the bare soil. This is the vegetated soil with more water vapor forming as clouds. You see this cumulus clouds or cumulonimbus clouds, convective storms. These are really rich in moisture, and if they have right ingredients to fall as precipitation, it will fall. That's what this diagram talks about. So alternate dry and wet patches, behaves in a slightly different way. And now when you have these dry lines to be really longer and bigger, and when there is short grass instead of really, thick vegetation, you have less evapotranspiration or latent heat flux, and it creates less cloud. In two different scenarios that we are talking about here. So cloud formation is important. If there is no cloud, the sun directly comes and hits on the ground. If there is cloud, of course, part of it gets reflected back, and anything that's trapped below the cloud layer is going to remain. Greenhouse gas effect that we talked about. These are all important concepts for us to understand for heat waves. And another illustration of my own research, what we did, applying land, irrigation on the field, we looked at how the thickness of the planetary boundary layer grows. Okay, with no irrigation and with irrigation. With irrigation, you see the clouds forming closer. So the thickness of the PBL on an average is 1,000 to 1,500 meters shallower, right? With no irrigation, with irrigation. With no irrigation, the sky is really open, really tall. And again, it's another illustration of the same graphic I want to say here, but then the concept here, heat budget that I'm talking about for bare soil, which I already explained, where you have no vegetation, the radiation that comes here partitioned into different components here, right? So more of sensible heat flux, turbulent sensible heat flux that we see here is happening, very less latent heat flux that's happening. But the opposite is true when the land cover is full of vegetation. You are talking about plenty of moisture, we have assumed like that, and then with radiation, this heat pumps, trees are heat pumps for us because they take the heat, they suck up the moisture, they transpire, they convert that into water vapor. And you can see, the latent heat flux is much bigger, and this turbulent heat flux or sensible heat flux is smaller here in this case, with the vegetation on the ground. So these dynamics, how the surface cover is playing a role for heat budget is important. The same concept, evaporation, or how the runoff is partitioned. When you talk about water budget, the difference between energy budget and water budget, we talk about watts per meter squared in energy units for energy budget. For water budgets, we talk about depth units in millimeters of water. That's the only difference. But then in the water budget, you are talking about precipitation changing into runoff, ET, soil moisture, and all that stuff. You are all familiar with that. So the idea here again is that trees convert precipitation effectively into water vapor. And that's very important for keeping our sky with or without clouds. Urbanization causes increased cloud base height, which is again reinforcing what we are saying so far. What do we mean by that? Urbanization with no tree cover on the ground we are talking about less evaporation. The cloud base is really taller, it's higher, right? Which is what we saw from before. So that same concept is written for a city called Los Angeles. And then what happens is it creates less fog, decreased fog. And when there is less fog, obviously you are talking about, you know, fallback effects of not trapping the heat, cool conditions, and things like that. It's another complicated diagram. Please bear with me. I'm not going to go into the detail, but I wanted to introduce you to the concept of feedbacks in this process. We will take one variable. There are lots of variables here, right? This is radiation budget, let's say. Radiation, latent, sensible, ground heat flux, downwelling, long wave, incoming short wave, long wave, and all that. Soil temperature, air temperature combined with albedo. So I'm going to start with net radiation. Just pay attention for a minute. We'll just quickly wrap this up. Net radiation, which is basically the available energy after subtracting the losses from long wave, long and short wave outgoing. This is the amount of energy available to work with. Either plants take it, convert water into vapor, or soil is getting heated up as soil heat, or it is used for heating up the air. Those are the three things that happens with the net radiation, right? Now, think like this. This dark line means it's a positive feedback. When you have plenty of energy, what happens if you have sufficient moisture, we will have more latent heat flux, right? More latent heat flux means, we saw that before also. When you have energy, when we have no shortage of moisture, the feedback is direct. You will have more ET. And that means you're going to have more pumping of moisture into the atmosphere as water vapor. You're all with me, right? Up to this point? It's simple, right? I've been repeating the same point. Now, let's look at cloudiness. It creates atmospheric moisture, means it creates cumulonimbus or altocumulonimbus clouds or whatever in the atmosphere that we are talking about here. So, this is all positive feedback. So, more radiation, more heat, more atmospheric moisture, more cloud, right? So, that means, of course, now we are talking about the other effect here. Basically, when we have more latent heat flux, it is taking that moisture from the ground. So that means it's depleting the soil moisture, right? So that's a negative feedback, because this dotted line that I'm talking about is a negative feedback. Okay? And that's also leading to so low soil moisture means we are talking about albedo that's getting low. That is actually increasing the shortwave downwelling radiation here. Downwelling shortwave radiation is increased when the soil is relatively having low albedo. Okay, and then of course the other part of this energy cycle, net radiation, is either partitioned as latent heat flux or sensible and ground heat flux, right? So we are talking about more energy means more sensible heat flux, also possible. That means more air temperature, hotter conditions that we will have. That means you are talking about no clouds, radiation loss is much higher. In the nighttime, that causes more cooling. And ground heat flux is, of course, more energy means more ground heat flux, and that heats up the soil. This is a positive feedback that we have. This happens on a daily basis. This feedback process happens on a daily basis because of the sun, depending on where you are. In a forested area, it may be different. In a bare soil area, different. Urban area, it is different. Likewise. The other part, there are three things here, but I will start with the simple one, tropics, because we belong to this tropics and subtropical area. We will not worry about northern high latitudes for this. Just again, look at these two diagrams for a minute. We will start from here. Vegetation. V stands for vegetation. Green vegetation, okay? When you have more precipitation, this positive feedback I'm talking about, it's going to create more greener space. Calicut is an example, Kozhikode is an example, or Western Ghats is an example. You have plenty of rain, plenty of vegetation, right? That's a direct connection. You don't see more vegetation in Sahara or Thar, but you see here in plenty of rain, raining places. What happens then? Positive feedback here. What is E? Evaporation or evapotranspiration. That's also going to be more because of plenty of moisture. So I call this as a positive feedback, hydrologic positive feedback, because more rain, more vegetation, more evapotranspiration. This is a cycle. This is one part of the loop. And again, we are repeating from before all of these concepts, right? Now, with this vegetation, you're also talking about absorption of solar radiation. Green cover sucks up all the solar energy. Okay, that's a positive feedback that we have. When you have more absorption of heat that's available, when you have plenty of moisture, that's going to convert that into evaporation for plants. So that's a positive feedback. Looking at the radiative budget here, the same concept, vegetation increase to leads to delta E, that is E increase leads to delta P increase. And the radiation budget is increasing, which gives you more precipitation again. So it's a positive feedback. Let's not worry about the albedo cycle, especially in northern latitudes where we have sea ice, ocean ice, and all that concept that we don't need to worry about in the interest of time. But these feedbacks are primary reasons for what we call as a heat wave. Okay, what we call it as a source for heat wave. And heat wave is not a small confined area, right? We are talking about happening over a large area driven by larger circulations from beyond the region of, for example, India. It's a prolonged period of drought, right, or dry conditions, abnormally high temperature relative to the climatological norm of a region. That's the basic definition. It does not stay just for a day in some cases, it can go for several days. And also, people measure this with respect to apparent temperature, air temperature, or wet bulb temperature, which is basically a concept where they combine humidity and radiant heat to come up with wet bulb temperature to represent the heat wave condition. You see this heat waves in India. This is a little bit of a dated report, but the concept is still the same. Every May, April, May, we are seeing the country is literally baking, right? We just to recall your attention that we had before, heat wave, a departure of 4.5 to 6.4 from normal maximum temperature, right? And severe heat wave means departure of more than 6.4 degrees Celsius. We see this regularly. And what causes this and why? I mean, that's important because, I mean, it comes over a large area, particularly for a country like India. It creates a lot of casualties, a lot of, mortality, deaths. Basically, you see in the future, this is for the paper that those who are interested in furthering heat wave related studies, I just wanted to put this up here. Basically, they look at under future climate scenarios, how each country will suffer based on all the factors they are considering in this paper. But I just show only the results part here. India is showing up in red color, more or less between 15 to 25 or 29, net increase in the mortality rate because of heat wave. It's a big number. We have a big responsibility here really to understand what's going to happen to India. How can we protect or adapt to those conditions? This is not like happening because of the radiation budget that I said before, but keep those thoughts in your mind. That's also relevant for this, but it's also added to urban heat island part that I'm going to talk about later. This particular event that I talked about, 2016, the previous slide, they actually looked at more closely by running these meteorological models and saw why it was happening. Both north central India and also the coastal southern India was worst affected during that time. And then I'm not repeating this whole thing here. What they found out was the anomalous condition in North Atlantic here created a block that created a block here and making this North African anomalous high temperature to come into the region, including South Asia, including Central India, North India, during that time. When that was happening, the anomalous condition in North Atlantic, there was also cooler condition, anomalous cooler conditions in the Pacific. was simultaneously happening. This is Pacific here, right? And that created a block or anomalous condition for northwesterly winds to come. Because, of course, um, when we are talking about northwesterly winds, it's coming over dry area. Thar desert or other places, when the air mass passes through, it's going to have no juice in it, no moisture in it. It's going to be dry, hot air coming, and it was hitting the southern part of India at that time. So that was a double whammy situation in 1 year because of larger circulation anomalous conditions that we had both in the Atlantic and also in the Pacific. That was the setting for the heat wave. And now you think about the feedbacks that we have, because the heat is trapped already with these feedback loops that we are talking about. Under drier conditions, when we have all the heat is converted into sensible heat flux, you feel uncomfortable, unbearable. That's what happened that time, and people really lost life. And it's a bigger so whenever I'm talking about heat wave, you think about this. There is a larger setting that really sets the stage for the heat wave to come to the region, or the heat is getting ready to affect the area. Okay, so we talked about MJO, Maiden Julian oscillations, and then ENSO, Indian Ocean Dipole, in the second day or first day. Of course, these are the drivers that really matters for India. For El Nino year versus La Nino year, what the high pressure is, where the low pressure is, how Indian dipole is in the phase, positive or negative phase, and how these circulations are going to be impacting the monsoon flow. Whenever we are talking about these circulations abnormal, we start realizing that in the pre-monsoon time, which is probably around March through May. That is the time that we see increased temperature and all these circulation patterns abnormally behaving, creating the stage for heat wave. So connecting all the dots here with respect to bigger global circulations. And of course, we clearly see during the last 50, 100 years, it is intensifying just based on observed records. But then they've also found out from the model, from the same paper that I'm talking about, heat wave is kind of significant. 1.5 times, at least 1 to 1.5 events of heat wave that you will see for the entire Asian continent, almost. That's a huge problem. That's a huge problem that we have to be, handling. And it's having the impact on the human health, right? Health risks, including dehydration, cardiovascular strain, and increased mortality, especially when nighttime temperature remain high. I mean, we want to see the fluctuation, right? When the sun sets, all this radiation that's not coming should make your place cooler, but that's not happening in urban areas particularly. And then, again, when you are not used to having that fluctuation of 40 degree in the daytime, nighttime of 28, 25, but now you see whole day of 40 degrees, that means how many hours your body can withstand that kind of a heat. That's a heat stress, right? That's what is happening. This is not just for humans. It impacts agriculture productivity, labor productivity, because hard working people working outside in the field, they cannot really work comfortably. A lot of deaths happen. These laborers don't protect themselves and they die. And many regions in South Asia approach periodically dangerous wet bulb temperature every year. It is connected to urban heat island. It is connected to urban heat island, so that's why I wanted to kind of tag along this topic to heat wave. But I want to stop for a moment here to see if you have any questions or comments that we discussed so far. Anything that is sticky, not clear in your head. Feel free to stop me here and ask. I think this is the basic stuff that I was talking about with respect to feedbacks. For those who are new to the topic, probably getting to know some amount of the concepts of um, feedbacks. So if there is no question, I cannot see where it's coming from. Okay. Yeah, in one of the slides I showed the dry land compared and right next to a vegetated land. Um, That's an important question. I mean, this this is only happening on a regional scale. 50-kilometer patch, roughly, we are talking about, is sufficient to create this kind of distinction between alternate wet and dry conditions or vegetated versus bare soil conditions that creates enough confusion for this water vapor to go up in the sky from the vegetated surface. That unstable atmosphere that I was talking about can happen. But does it happen all over India? No, probably not. That is not the case. But now think just this 50-kilometer patch coming with the heat wave, because of the anomalous conditions of circulation that we have beyond this area. It is sandwiched with already this troubled bare soil heating conditions, and then the bigger atmospheric circulation impacted anomalous conditions can add to it. It really blows up. It really blows up. I don't know if that was the question that you had in mind. Okay, so two things coming together really to make your place uncomfortable. One is local heat, and then bigger area when we talk about heat wave coming from circulation anomalous conditions, it can also create problems. So now I think we will talk about urban heat island because of all the modifications that we have, roads, rooftops, pavements that absorb and store more heat than the rural areas, right? So that's what is happening when we develop the area. But if you look at the contrast between natural area versus urban area, there is a big difference, up to 5 degrees Celsius difference in temperature that you can see. Any city for that matter. But then how the cities handle that heat difference is the question that we are going to be dealing with here. Okay? About 4 to 7 degree increase in temperature in urban areas that I see from the literature. And then we also call the flux of anthropogenic heat on local climatology in human populated areas may be large. Anthropogenic heat, how do we define that? Basically, it's done in the model framework, which requires the surface roughness. What is surface roughness? In a vegetated area like here, wind does not flow that much because of all these trees, buildings, and this and that, right? So it kind of gets, the break. Um, Whereas in the open land, that the roughness is very minimal. So based on that surface roughness relationship, they calculate Z sub O. Basically, it's basically uh, the coefficient representing how much of a area that is developed, building area over the property size as LP in this equation that we are talking about, and the average building height that we have is used, like for a city like New York or Shanghai or Delhi, Mumbai, you can relate to any city. It changes, the surface roughness changes, and that creates the problem of wind, whether or not it is stagnant or moving. And that cross ventilation of a place is very important to carry the transfer of heat. If it is stuck in one place, it's going to feel that heat dome effect, right? That's what we are talking about here. If there is enough ventilation, we may see heat coming from the land, but it's getting blown away by the flowing wind. That's probably not the case when you have tall buildings like what we have in this Fifth Street of New York or whatever, high-rise buildings that we see here. So, um, urban areas have more buildings, less vegetation, but now they are also in the green engineering part, they are talking about more vegetation to be brought in to balance that latent heat, sensible heat flux. So, come back to that previous concept that I was talking about before. So, energy coming from the sun in urban area is getting divided more towards sensible heat flux, right? On top of that, we are also polluting with fossil fuel emissions, air conditioning, and industrial activities that also increases the overall temperature. So those are two add-ons to the bare soil or urbanized area. Albedo. is a term some of you are familiar, but some of you probably are coming to know for the first time. So I wanted to introduce this term here to tell you this, that when we have low albedo, most of the energy is getting absorbed. Condition like this is vegetated area or a wet soil condition, most of the energy is absorbed, right? So albedo is really less. It's a measure of reflectivity, so there is less reflectivity when you have low albedo. The opposite is the case. White snow or ice, when the sun comes and hits and it goes back full 100% or 90% or 80%, high albedo, when you have high reflectivity. So, urban areas, of course, is in the middle somewhere, but for the most part, they are not going to absorb the heat. They are not wet soil, right? They are not vegetated. That means that energy that's actually sucked up or coming into the land is somewhere heating up and remaining in the area. That's the heat dome effect that we have because of the albedo. And this is all used in the model to reflect the heat conditions. The other part for heat island effect is the way how the city is designed. For example, I'm showing all the cities from the report that I got from, National Climate Assessment, fifth National Climate Assessment report for the US. So all the cities that we have, whether it is Seattle on the Pacific Northwest to Chicago in the Midwest to Washington D.C. all the way to Texas in the South. But you see here there are layers: compact high rise, compact mid rise, compact low rise, and then open low rise and heavy industries. So high rise really stacked up one close to the other, like New York or Seattle or Chicago, creates these urban canyons or trapping places for wind not flowing and no air mass that's actually coming in and out of the area. These geographies or the way how they orient the city determines the wind flow, the intensity of air stagnation, and the ventilation aspect of it. So urban roughness increases turbulence in the boundary layer but often fails to disperse heat at the street level. Bigger, at the higher level, it creates turbulence, creates unstable atmosphere that we talked about before. But at the ground level, or probably at the height of these buildings, you see more or less static air. That's also when the heat is trapped there, it really increases the heat condition. So geometry is one factor. Okay, and then water versus energy partitioning, meaning how much of that heat is being spent because the city has got more buildings. Regardless of the geometry, you are talking about increased temperature compared to one without buildings. With water bodies or vegetation, you see even the cool effect here. The temperature is not even showing up. There is no rise in temperature because of daytime heating. So we are also polluting because of our activities, vehicles to industrial pollutions to everything. And then heat retaining properties of these buildings, asphalt, rooftops and everything takes more heat. It emanates very less heat back, at least during the daytime. In the nighttime, the opposite is the case. It releases quickly, and sometimes you have urban cool islands effect that you can have. And this matters for understanding the urban heat island. The one other concept that I wanted to say here is the day-night urban heat island dynamics between rural to sub-rural or sub-urban residential to commercial downtown with all these high-rise buildings. Okay, again, the rural area. Think about this. Basically, you have tall clouds and increased temperature in the middle of the downtown compared to the rural areas. The boundary layer thickness also changes as we saw before. Now we have to relate the previous concepts that I said before. Because of vegetation, because of ET, because of cloud formation, talking about BBL thickness to be lesser for rural areas compared to urban areas. That's a setting for urban heat island. We are talking about all these combined green space plus built up area, partitioning of energy with and without moisture on the ground makes the case for urban heat island. So that's the summary from this slide that you have here. The other tangential thing that we want to be saying is with more heating, more direct sun going in and out of the area, you have less fog, right? Fog decreases. I showed you another paper from Los Angeles where they say because of urbanization, they have less fog. That's also a problem. That's a problem, right? Creating more of a, urban heat island effect in the urban areas compared to rural areas. So cloud fog interaction is very important to keep the place cooler compared to, the place making it really hotter. So this concept that you want to remember, and then again, this is a good paper that I put here for you to refer. Impacts of increased urbanization on surface temperature, vegetation, and aerosols over Bengaluru. It's a recent paper, 2-3 years ago. Good concept. I mean, as you can see here, the summary from graphical abstract that I got this from. Daytime, nighttime, between monsoon and dry season. Before rain, this is during the rain. Urban areas get the same amount of rain as non-urban areas, daytime, but the aerosol effect, of course, is not that prominent, but increasing trend in aerosols in the dry season, right? Because there is no rain that comes and takes away the dust and pollution and everything. But in urban, non-urban areas, rural areas, you have less aerosol problems. So this is the dynamics that what we are talking about, whether it is land atmospheric interaction feedbacks and how the circulation happens and how the daytime heating happens because of that and what kind of surface roughness creates this condition for urban heat islands. Okay, nighttime, no big deal. Both areas, urban, non-urban areas, are going to be the same. But when we pollute in the urban areas, you have, of course, dry season, more aerosols, and not much of a problem. So keeping the place greener, have less aerosol problems, more insulation from urban heat island effects and things like that. That's kind of the message I wanted to say here. And of course, people are now coming up with this concept of how much is the space that I have to have as a green area to break even, to make sure that my urban heat island does not come through, or I'm able to partition the incoming energy effectively into latent sensible heat flux ratio. And this paper talks about it. I think they compared between Shenzhen and Hong Kong, which are the two neighboring tall skyscraper cities. Very good paper. They came up with about 2.71 as the threshold to say, like the vegetated over impervious area threshold that they want to have. It may be different for every region, but that's something of scientific interest for someone to pursue in this crowd if you're interested in doing that. That is something really useful to know how to keep our place cool, how to keep our place green, based on this kind of studies that we can really come up with this understanding that we talked about before with respect to feedbacks, with respect to radiation budget partitioning, right? Little bit of understanding on the atmospheric side, but not much is required. But this is more on the side of hydroclimatology, hydrometeorology, with more on the land surface part emphasis. Okay? So now somebody was talking about concurrent disaster or compound disaster that we will talk about also. This is an example of compound event, right? We are talking about heat wave, already a disaster, and urban heat island that we create on a local scale. When they two merge, it becomes a compound disaster already. For us to understand how the cities will suffer, and of course, this combination makes it even worse. We want to see daytime going up, nighttime temperature coming down, but that's not happening. When these compound disasters happen, we are talking about uniform temperature for 24 hours, which makes it very, very difficult for people. Okay? And dense building trap heat and create self-reinforcing heat stress conditions. That's compound, heat problems. On top of that, we are talking about climate change. So now we talked so far only about the landscape change, how the day-to-day activities of sun and our anthropogenic induced changes on the landscape was creating this urban heat island with climate variability. I would say the circulation as climate variability. Added to that, we are adding temperature from climate change perspective. right? That's another layer of complexity. We are already talking about average summertime temperature by 1 to 1.5 degree more for India. So the baseline itself has shifted now on top of all the other problems that we will have. So climate change is going to be a multiplying factor when it comes to heat waves and urban heat island problems that we will have. So case studies in India, for example, there can be plenty of studies that's already done, but you can also pursue some of those things. And there are examples in the US they do every year because one particular event, what happened last year in February, for example, um, there was a high pressure dome north of Pacific Northwest, and that created the heat wave. You remember I talked about jet wave coming down in the summertime and receding back to the Arctic in the winter time. Same as India, I think we showed some circulation patterns for India also. Um, I think 10:20. I'll take 5 more minutes to finish this part. Um, this heat was so unusual. Place like Chicago in the winter, it freezes. You cannot even go out without multiple layers. You get frostbite because of wind chill, -20, -30, or something like this. It's called Windy City. Those places, I don't show the photos, but interesting photos I had from these reports. People were biking under the sun with no jackets last summertime, last winter, especially in February. That's because that high pressure circulation that blocked, the Arctic air mass coming down, so that heat from the south was going up, heating the whole area. So it changes the dynamics. So circulation is important, climate change is important, how we keep the cover, grass cover, green cover is very, very important. So all of those things combined, I could only touch the surface of this topic. I have to admit that. It's only the surface part, tip of the iceberg. But there is so much in this literature, whether it is heat wave analysis or whether it is urban heat island effects, you can take it up further. When you read more based on the discussion that we have so far, you can at least expand based on specific area, specific science question that you would like to have. I hope I did justice on that part by giving you some orientation about the topic. Do you have any questions for me? Well, it needs a combination of both data and models. So you have to understand how the heat is partitioned for a given locality and see how much of heating that's happening at the local scale, how much of energy that's converted to sensible versus latent heat flux. There is that Bowen ratio tower is available to do these measurements. You can populate in certain areas of the city, whole city, and come up with understanding where the Bowen ratio is high, where the Bowen ratio is low. That is the first point. On top of that, some. Oh, yeah, yeah. Oh, yeah, yeah, yeah. And then on top of that, you want to also bring in the models because, like I said, the heat effect is not local. There is some other settings that's happening surrounding that. So to bring in the air mass or to bring in the circulation, to understand how the low pressure, high pressure zones are operating for a given season, for a given region, you need mesoscale models, atmospheric models that I'm talking about. Or they may have the outputs already, but based on those conditions, you can see for a given time how much of a heat that is transformed into latent sensible heat flux for a given season. You may have to observe that for a given season and then see, do we have enough cover? Do we have enough vegetation? How do we organize the city to make sure that wind flows through instead of getting stagnated? So it's a urban planning, city and urban planning that people are talking about here. Um, you know, all of those combination of factors. Interesting science journey that one can take through this. It's transportation related to some extent, but it's also related to how we modify the landscape. So there can be planning done based on these kinds of things. If you want to keep the city cooler by 5 degrees, what are the effects? That should be the objective. I'm seeing a temperature increase between dry season versus monsoon or cold season versus dry season. And then how can I quantify um, this green patches and what can we do to make sure that temperature increase is not huge, something like that. I'll stop here, but we can continue this conversation if you have anything. But let's go for coffee break. Come back and start talking about landslides. I may not take more than 45 minutes, I can promise. A lot of interesting stuff on this too, but we will talk later. This is kind of a last lecture on the topic of extremes. But I have other assorted topics to talk about, but I don't know about the interest level. But I will survey you whether or not you want me to discuss those topics later. But depending on the time, we don't know. Those topics are something like how to do research, how to set up the questions, research questions. What do you do for, you know, analysis, or how do you publish? Those are my general topics of interest. I talk to people around, whenever I go to different places, I give this as one lecture as part of the whole plan. But this time around, we did not plan that. I don't know whether there is interest. Uh, Raise your hands. How many of you are interested? Oh, good number. Okay. Okay. Um, I'll see if I can carve out some time just to, borrow time from other speakers. 30 minutes or 15 minutes. Not 15 minutes. Definitely I need 30 minutes to kind of go through like how do you do all these things and publish. For publication, there are some simple examples. I mean, AI will do some things for you. I'm not saying that. You need to have a good idea about how to take the direction. You are a director of a movie, right? A paper is a movie. And how do you tell the story? Those are the things that need some skill, some planning, some management of ideas. So I will kind of walk you through that. It will not be in depth because 30 minutes is not sufficient. But since you have interest, let's figure out if there is a way to accommodate that. Hmm? So I will kind of finish my talk for this morning with landslides. Which is an important topic again, but I have to go to the basics again to start with. Like I said before, on precipitation extremes, which is a trigger. I mean, landslides does not happen in isolation, right? I mean, the trigger is enough rainfall, ground cover that is saturated, the soil layer, and then the slope stability part comes into play. But for all of that, what are we looking at now? There is this paper that I think I may have mentioned, but I found this slide, so that's why I wanted to show you. Somebody talked about concurrent changes in extreme events. This paper is of use for you. The other one, seasonality, intensity, and duration of rainfall extremes. It is changing. We all know that. But how much is it changing? How much is it changing in Wayanad? How much is it changing in Chennai or Coimbatore or Kozhikode or wherever? That is a site specific information of that IDF, intensity duration frequency analysis, and see how that 25-year storm or 50-year, 100-year storms are moving. They are not coming now in every 50 or 100 years. Now they are coming every other year, every 2 years, right? So that frequencies have already changed. The intervals have changed. So we cannot keep this literature even. This is probably a little bit old. So if you are doing the analysis, that's where you should start with for landslides and for flooding. It's also related to flooding, right? So we're talking about this. So in the US, they are talking about extreme rainfall statistics may shift with thermodynamics properties of air, which keeps more moisture in the atmosphere, which we talked all these 3-4 days time, right? Glaciers, Clapeyron, relationship of 7% increased moisture that you have in the atmosphere because of thirsty atmosphere, dry atmosphere, heated atmosphere, right? And of course, these papers are talking about the evidence, connections between what we see on the ground and what the theories are establishing as rainfall extremes. And yesterday was wonderful exercise for you, given by our CAWRDM scientist, right? He gave a wonderful, Naveen, Dr. Naveen, um, use that data, use that technique for understanding what kind of um, shift in the extreme events related to precipitation, particularly if you're talking about only landslides. Multiple of those indices can be used ready-made. He showed you with ease of how to run even on the cloud. You don't have to download the GitHub. The time limitations is there, but still, if you want to download and set it up, thorough analysis of extreme precipitation events, 95th percentile, 99th percentile. How have we changed in with respect to CMIP 6 data? That's an important part that you have to do if you want to come up with an bold statement. This is a bold statement. Extreme rainfall statistics may shift as the US climate warms. I want that kind of a bold statement coming out of this analysis for site specific work that you all do. Okay? This is the theory part that I was talking about. So we are looking at that, shift in precipitation. I think I showed this paper before, but I put it up here for your reference. You can refer to that later. So the main thing is not just using the model as black box. Even when you do that, what is that, climb pact or whatever that version that you used yesterday, you have to ask the question, why is the data showing this? What am I interpreting from this? Cannot just keep your focus only very narrow. You have to really broaden it up. Unless you ask the question of why, what, how, where, when, then you will not get an answer that will not be curiosity driven. So make sure that you ask those questions, but process understanding with the data is very helpful. With that paper that I am talking about, gives you what happened with respect to the first law of thermodynamics, second law of thermodynamics, how the lapse rates changed, how this instability happened, what kind of cumulonimbus clouds formed, in area like Kerala, and identify those scientific questions, and make sure that you kind of infer the results in a right way, and relate to some of those things that are highly confident already. I'll talk about that part, hold your thoughts on that. When I'm saying highly confident, there are some processes based on precipitation or temperature are highly confident. We can say for sure that this is because of temperature change or precipitation change. So you should be able to have that causal relationship established with your data. Okay? Again, this is another source that you might be interested, but I have not checked lately whether or not this site is still working. There are tons of indicators. Basic stuffs are here. In addition to the climb impact or climb pact yesterday that you saw, this particular site gives you multiple indices that you can use, including climate indices that we are talking about here. And the confidence part that I'm going to talk about here, we are very good with respect to attributing to climate change, anthropogenic, human-induced climate change, to extreme cold or extreme heat, droughts, and extreme rainfall. So far, the confidence, that's of course, this is at the high level, confidence and understanding the effects of climate change event type. So this sits at the top. So when you are talking about heat wave analysis or drought analysis or extreme event analysis, you can say for sure with these climate models that this is because of climate change, what we are seeing. That is the confidence that they are talking about here. But do we have that same confidence with our local scale processes in some of those things is a question that you have to ask. Like for example, landslides happened, is that because of climate change or is that because of some event that really added to all these things? 20 inches of rainfall, 540 millimeters or so Wayanad received in that short span of time, probably saturated the soil column. Is that an average number? If not, what caused that increased temperature or precipitation? That is a question that you should be asking. Then you relate that to attribution part. Attribution, we don't need to worry at this point, but what I'm trying to say is if you are picking one of these topics here, you can certainly assure yourself that climate change is playing a big role, big role. Okay. Again, Now, coming to one incident, I mean, it's not something that I'm picking for a purpose, but this audience is familiar because this is in your backyard, most of you. So I thought I will just start with this. This happened last year, so some of you really remember this fresh in your memory, right? It's about a year and a half old news, originated here, and I think it came all the way to the south, I guess, right? I mean, this, I'm hopefully not mixing up the direction here. This, is it Mundakai? Churamala, Vellarimala, something like that. They are saying the three locations around this area that saw the landslides triggered by extraordinary rainfall. That's the trigger for a landslide. So I started talking about the trigger first, right? So you need to have that. And what caused that trigger? Again, how did this monsoon rainfall came in? Should it have crossed already Kerala and gone to inner lands? We don't know. So why was it stagnant? How much was the rain normally? Is that the aberration or a variation from the long-term average even for the monsoon season? How much was the variation? Can somebody tell me? What was the significance or what was the shift in the amount of precipitation typically for that time of year between 2024 to previous years? Anybody had done that analysis? That is something, curiosity aspect, right? I mean, you have read paper, you have watched news, you know how much was the rainfall that we got. Did we ever calculate what was the shift in the magnitude with respect to rainfall quantity compared to the last big event? Or what was the return period of the event that we got? Is that 500 year event or a 1,000 year event? We don't know. That is a nice analysis to do, to understand. Nice paper can come out of that, but there are plenty of papers already are there. You may want to first collect all of them and see what they are saying. And then if any new ideas that you come up with, something to think about, because this is not the first time that you see, it's not the last time. You are going to see this many, many times. Sorry to say that, but it's going to happen, right? So, how are we preparing ourselves as scientists to do this kind of analysis? So, these are some of the things I wanted to say, but rainfall is the first thing, right? And then it has been described as one of the deadliest landslide. 300 plus people died, right? It's unfortunate. The affected terrain is steep in the Western Ghats with tea plantations, forest, and hillside settlements vulnerable to slope failure. These are from different sources of rainfall, I mean, data sets and published reports. So the rainfall was the trigger. Geomorphology and steep slopes of the region was a big problem. And prior land use made the slopes unstable under heavy rainfall, right? I don't know all the details, but I think from the reports, what I gather is that human land use change, like deforestation, hillside agriculture, modified drainage, and scattered settlements, reduce natural slope stability. I will show you a video. I think you saw that video before, that super floods. In that, I kind of intentionally stopped at one place where they went and really showed how they fingerprinted the landslide event in one of those North Carolina floods. I want to show that because that's the kind of fingerprinting that one has to do. Geologists in this crowd, if somebody is interested, go to the field and collect that kind of information and see what triggered, where it started, how did it start, whether it's direct percolation of water from uphill and showed up downstream. Like yesterday we saw, I cannot remember the Malayalam name for that, but like pipe flow, underground, that I think it moved and then it showed up a spring somewhere outside. So caving the whole area because of that pipe flow. So, sorry? Soil piping, but Malayalam term I forget. I may have the photo of that taken. Do you remember? Anybody remember the Malayalam name that we saw in the museum? Surangam. Yes, Surangam. Right. That's the exact word I was looking for. So that happens, maybe in the Tamil also, I think that is the same thing, Surangam. But the main thing is how that was started, how it created, and was that the reason for slope stability or instability? Something to ask. I mean, we have already done that kind of analysis historically or understood that kind of a problem in a mountainous terrain. Are we doing that now to understand, reconfigure the same concept? Something to think about. Now, poor early warning and evacuation also adds to the problem. In addition to understanding the physical mechanism and what caused, unless we know how to communicate the risk, that is a big problem, right? So tomorrow, I think we are going to be talking about early warning system. Dr. Pramada Madam will talk about that. But you see, in our super floods analysis also, prediction of floods is only half the story, half of the preparation. The remaining half of sharing that information, how all the cell towers lost power and collapsed and they could not even reach out with all the highly sophisticated model predictions they had in the US, could not get to the public. So they lost lives there, right? The opposite is the case for Spain, where Valencia, they talked about the flow stations that were measuring the flow got knocked out. The sensors were out of the picture, not collecting the data anymore, flown away, blown away. So um, the loss of communication. So early warning systems you may develop sitting at your office, but then how do you make that available to the public? Not just one way. I think somebody talked about evacuation routes, right? So what I would think is, of course, in the simulation world, when you're talking about evacuation, you could do multiple, option 1, 2, 3, 4 kind of a thing, and see what is the best one that is foolproof, that is, disaster proof. You know, taking examples from those three, case studies that I showed. So these are the reasons that happens with respect to landslides, right? So before and after, you see how much of opening that we are having, big area getting opened up, destabilized banks, maybe erosion on the bank sides, and then caving in, and lots of damages that we see. So, I mean, ultimately it gained. I mean, we talk about three things: mass, energy, and momentum. All three happened here. When we are talking about initiation, right, and how that basically gains momentum with mass added up, and you could see that happening. Another place where we see, as of this year or last year, is Uttarakhand. So we've seen that Darali, I think, is the region that we saw. And then 2, 3 years ago, we had the same thing in Chamoli, so in Uttarakhand. So these are the vulnerable places for landslides, right? Because of combination of factors. You cannot just say only one thing like development or that is the reason deforestation. No, maybe something else. So you as a scientist want to really give a holistic picture. I think I wanted to show this even on the floods discussion, but I just show this here. Our ultimate goal was to say real-time forecasting. That caught my attention as of this morning. That's why I brought this slide back. We did the study, right? I told you about capturing all the tropical cyclones that starts from Gulf or Bay of Bengal and then coming into these two river basins, Nagavalli and Vamsadhara. And we kind of created, a portal inputting all the data here, coming up with a prediction. It's not real time. We come close to saying it as a real time, but we don't have data. This is from NRSC inundation area that we could get from remote sensing. But we need depth also. We don't have the depth information to release or provide alerts to people saying your area is going to be underwater by 5 meters or 3 meters. So that needs full scale analysis of floodplain modeling, hydrologic and hydraulic combined modeling. I will show in the last few minutes of what we try to attempt to do, but some of you might be doing in the same line. But I want to show this paper, and this has got some useful information. So I put two papers here, but you can refer to Google Scholar and see additional papers. I think I showed you this thing before, but we are saying that for disasters, technology is very, very important, right? So this particular one talks about, the use of drones. And we also used drones in the Chamoli study. Just to recap or give you a basic information about Chamoli disaster, it happened on February 7th of 2021. There was a huge glacier. I don't know whether you can see that from one of these figures. It's somewhere upstream here. Oh, yeah, here I can see that. So this collapsed and it fell into the Rishiganga river, and then it joined with the Dauli Ganga, and it started flowing downstream. It blew away the bridge. I will show you the photo of that bridge. And then Rainy Village got affected, completely separated because of that road got destroyed. And there was a hydropower site that got damaged. Some people, number of people died, and this is a flood combined with landslide issue. It's not land in this case, landslide. It's glacier collapse, similar to landslides, but of course you need technology. 4 years ago, I was lucky to go there and with my colleagues, bunch of colleagues, and this is Dr. Padmanabhan from VT India is here. He brought this drone from Chennai all the way, and Dr. Kansal from IIT Roorkee, and I forgot this gentleman. He's the pilot. Dinesh. This is Dinesh. Forget. So we all, this is the Uttarkashi, Joshimat Bridge, downstream-most point where we have flow stations and we could actually collect the flow data. Right below is the Ganges. Okay, and we flew the drone, combination of the multiple two nation collaboration here in this case, US and India. And we flew drones in this area, which is a marvelous experience for me personally. It's a big one. We carried all the way, they carried, lot of effort bringing to Himalayas. And then we measured the flow in the river. Okay, we measured what was the velocity because we wanted to really use this data to calibrate the model, HECRAS, for example, in this case, and want to understand how to measure. And it's very difficult. Water is chill, high velocity water. It's not too deep though, but velocity is ferocious here, and it's even more, high in other places. This is the Tapovan Dam. You can see the tall mountains. These are 9,000, 10,000 feet tall elevation. And we were driving through all these cliffs, the high roads. We were able to see this. We were not allowed to go and collect the data, but for obvious reasons, security issues. But two gates that got damaged during the floods. So that's the power of water. And you see the same power of water in the landslides that I will show you in a minute with um, Wayanad. But what happened here is that this pillar, I mean, it looks small, right? This bridge file, it's a 10-meter wide diameter. I could not even hug fully. It's 10-meter diameter. I measured that. It's like a stick. It just blew away. That is the power of water. With all the concrete, you know, um, core inside, this bridge is not anymore existing. And the army came and temporarily put a structure here for conveyance. Because otherwise the rainy village on the other side, rainy Chuck village on the other side would be totally disconnected from the area. So we collected the soil sample for landslide analysis. Soil sample analysis is very important. We wanted to know what kind of texture, how much is the moisture holding capacity of the soil. How can we include that in the modeling analysis? That is the intent. These are two top-notch scientists from National Institute of Hydrology, Dr. Bisht and Dr. Mishra. Um, Bisht's paper is the one I repeatedly, so he's from IIT Kharagpur. I've been working with him for the last 10 years now. Wonderful scientist. His papers I shared with you already about, he did the rainfall analysis for the entire India. The drought paper that I frequently refer is his paper. So he's still, we work very collaboratively. And again, data collection is very important. Why did we flew drones there? Why did we use drones to collect data? I will come to that. But This is the model, SWOT model, which is not a great model for event scale analysis, but still we went ahead and wanted to know how much was the flow in the river. We ran the model, we partitioned rainfall into runoff, right? That's the whole idea of this class, that what we are talking about. Divided the basin into multiple sub-basins. We created DEM and watersheds. This is the important part. The drones that we use to collect the cross sections or the elevations at high resolution that we used in the model, and we kind of combine, when we used Landsat based DEM or digital elevation model, they were not defining the cross sections of the river correctly. So we had to come up with high resolution DEM. So we kind of wedded two products together, merged two products, DEM in the places where we cannot fly the drones. And in the places where we flew drones, we kind of use the DEM and combine those two together. You cannot fly drones everywhere. That's another problem, right? And these are tall mountains, 45 lakh worth of drone that you don't want to lose crashing in the mountains. So we had to keep the line of sight to be really between 300 to 400, 500 meters max. So we were able to fly that and collect the cross-section information, and we brought that back and provided into the model to calculate the flow. That is an important part. So I'll skip all of this here. So climate data, general, precipitation, temperature, and all that stuff we used. We come up with hydrographs. We'll do that today, not with SWOT model, but with HMS, hydrologic modeling system. Just some of you may be knowing that, but for some of you it might be new. How to generate hydrograph, I think, is the one that we will be doing today. So you will get to see how to generate this hydrograph, okay? And then we kind of use that in another model called HECRAS, which we will do today also. So we created this transect, this cross-section profile for multiple locations for every 100, 500 meters, something like that. And then, we calculated the velocity or water surface elevation, things like that with 1D model, but you can go for 2D if you have good information. And then if your floodplain is big, want to consider 2D than 1D, but 1D will do the job. What I mean by floodplain, you have banks, on both sides, but then you have areas that this river can swell and overflow, the floodplain that we talked about on the flood discussion chapter or lecture. So you can combine hydrology and hydraulics model to get to only part of the story. Let's say you did everything correct and you got this depth. Sorry for the image that's not showing up correctly here or color wise. Depth, velocity, and water surface elevation you can get from this model if you run it correctly, if your data is good. Okay, if you're confident that you are able to calibrate the model with real-time good information, then your success is almost halfway through. Then you get the depth of water, how much was the flow that was happening and how much was it actually spilling over the banks and all that stuff you can calculate. So we did that as a cursory analysis, but I will not say it's anywhere close to what we want to get there with respect to understanding flood flows or peak flows. But that's the first part for understanding the impact of extreme rainfall events, and then lead that to landslide analysis. Okay, so I will come back to that Wayanad part where I have a video to show. But before that, I want to say, because we are talking about compound disasters here, right? I talked compound disasters in the context of heat wave combined with urban heat island, okay, as one related one. But you can thread similar disasters, many of them like this. For example, in this case, drought and fire can come together. Drought is the trigger for forest to be really ready for burning, and then it starts burning. And then once fire starts, you have all kinds of aerosols leaving the landmass into the atmosphere. So pollution comes. So aerosol cycle, and then air quality problem comes there. And then also landslides. How can I say that? when you are seeing the drought landscape desiccating the vegetation and the vegetation is dead because of fire, we are talking about the land without life. So the rain that comes through, instead of getting into the soil, now it starts flowing quickly, rapidly. So that's another trigger. So that's a kind of a compound disaster that can happen with drought setting up the stage, with fire, and then landslides, erosion, air pollution problems combined. So the disaster happens. This is on the side of disaster side. Of course, on the governance failure, when I'm talking about, there are so many of them here, talking about how technology is used or corruption or whatever, that is not applicable in this case in the larger sense. But combining that with the disaster here to come up with vulnerability and exposure. Yesterday, if you remember, some of us were standing right close to the vulnerability map of Kerala. I think the scientist there in the museum was explaining that to us, and you all had some interesting questions to ask her also on why, Trivandrum was listed high compared to the other place or something like that. Somebody was asking that question. I forgot who asked that question. But the main idea there that she was telling was, um, hilly areas were prone for more landslides and erosion compared to the other areas. I think that's the message I got. But then there are other things like salinity or sea level rise impacting coastal communities to many other things that she was talking about, not just floods, but droughts also. So, compound disasters happen, and then there can be some technology or transfer of information. And now you know how these decisions are communicated to the public to create awareness to go to higher places or to avoid these places where we have problems, those kinds of things. And even on a real time basis, if you have to communicate them, what kind of methodology, what kind of evacuation routes that you need to have when you are talking about evacuating people from these disaster zones, everything combined here, right? We are talking about, a cascading disaster. This paper is editorial, it's not too technical, wonderful paper to read though, so that's why I put it here. But I want to go back to the video since I have few minutes time. One video that I have, I think I may have finished here. 1 second. Um, oh yeah. So the takeaway here, I'll finish that part and then to. So the takeaway, let's finish the discussion here. Climate change, land use change, steep terrain to to amplify the risk in the mountainous and hilly regions, and urban areas. If you're talking about heat waves and heat island effects, these extreme events are instructive for integrated hazard management assessment. First of all, we are talking about assessment only here, right? Impact assessment, very important. But you have to see them like what kind of combination of factors that are leading to that disaster. And then it also highlights the need for timely early warning. In Texas, as well as in Asheville, North Carolina, they had 45 minutes to 1 hour to 2 hours time, whatever it is, 15 minutes. That was not sufficient for some people to escape the danger because it struck in the middle of the night and they lost the communication power, ability to really relay everything to them. So again, the need for timely warning. So your science is one thing, but how do you quickly do it and how do you transfer that information to the right channel? It's not all in your hands. All I'm saying is when you're talking about research, or establishing some kind of a disaster management strategy, these are the things that you should be thinking about for resilience. Okay, and then for adaptation path, of course, we want to really look at how these failures are happening. Are we having our structures defined and designed based on the changing conditions, or are we really stuck in time, frozen in time to use the approaches that we have been using in the last 50 years? How can we adapt? What kind of adaptation measures that are required to do this? So Those questions might be of use for you. As a student, some of you may not really have to think about that far, but as scientists, some of you are here, you might know. I mean, doing science is one thing, but then how do you really communicate that message? And how do you really prepare, the infrastructure aspects, considering all these things into the future? That's all in your hands. So I'll stop there with respect to takeaway message on this chapter. But let's talk about knowledge checks quickly here. It's not comprehensive, but I think I mentioned this on day one. Now I'm going to go for the last day. So which factor most directly increases globally, extreme rainfall event? Is that increased cloud cover, changes in vegetation, Clausius Clapeyron moisture scaling of 7% increase, or solar radiation change? Solar radiation change? Clausius Clapeyron. That is the number one thing for extreme events, that what we are talking about, because it increases the moisture content in the atmosphere, it dumps the moisture back. Okay? Flash floods are typically caused by slow moving depressions, short duration, high intensity. I don't have to read the remaining two. The majority says B. Let's see if it's correct. It's correct. Riverine floods depend most on coastline shape, catchment size, and antecedent soil moisture, or number of storms per season, or atmospheric pressure. I hear catchment size. That's correct. Coastal flooding becomes more severe due to earth tides, sea level rise, storm surge, solar flares, and reductions in sea level rise. Let's see if that is the case. Okay. Great. Okay. So I think the question that I have here is already answered. I did not remove the highlights. So anyway, rainfall event exceeding 204 millimeters per day per IMD is categorized as extreme rainfall, extremely heavy rainfall. So we saw in that slide of down to earth report where they talked about 64 to 104, 104 to 164 something, and beyond that is extremely heavy rainfall. So these categories can change. Like yesterday, Dr. Naveen was talking about, for your condition, extreme event analysis could be you define. You could be defining that. I have few minutes, at least, another 10 minutes before I hand over to Dr. Pramada. But I will show you the one that I wanted to show before. Let me see if I have that still. Geologist, yeah. Stop. I'll just show this. It may not take too much time. I'm not going to show the whole video. You've seen this before, um, of floods in Asheville, Spain, Valencia, and then also in Texas. But they went back to Asheville mountainous area similar to our Wayanad region. So it caught my attention. So I thought I will show how they are doing this. I think they are explaining this nicely.
Over 100 years at a time. So people will build because they think that there's nothing that's going to happen, but actually it is a dangerous place.
It's a double threat. To stay safe, it's increasingly important for people to be aware of the risks. But the range of danger that floods and heavy rain present depends a lot on the terrain. In the hills and mountains around Asheville, the biggest killer from Helene was landslides. The National Oceanic and Atmospheric Administration classified the landslide deaths here as fatalities from freshwater flooding.
With this type of landsliding, what we saw with Helene, water is the key ingredient. None of what we saw happen is going to happen without a tremendous amount of water present in the soil.
Water from Helene caused this slide. Fortunately, no one was hurt.
It's absolutely the most acutely dangerous natural event that you see in the Appalachian Mountains just because of the speed with which it moves.
13 miles east of Asheville, the storm left another tragedy in its wake. In the
It's like
small
Kerala,
community of
right?
Craigtown,
It looks like this place.
13 people lost their lives when a series of landslides swept down the mountain, destroying homes. Geologists Jennifer Bauer and Philip Prince are helping compile an inventory of the more than 2,000 landslides in North Carolina, triggered by Helene's rain. Today, they are climbing to the top of one of the Craigtown landslides to find out what started it.
Can you see anywhere that might be a groundwater source up here?
Let's look under here.
This slide, like most in North Carolina, was a type of landslide known as a debris flow, a landslide made of soil, rock, other objects, and water.
So this is what, like, I don't know, 3 feet long?
That's a good way to concentrate a lot of groundwater in one spot.
Yeah.
For sure.
Debris flows often begin near the top of a mountain, where the slopes are steepest. Rain soaking into the soil can accumulate as groundwater high on the mountain. Underground channels can then funnel it to one spot.
This is a big hole in the ground that groundwater just comes out of. And groundwater can find its pathways through all of the loose boulders in the soil and probably shot out through the soil right here.
And with the added push from that providing almost like groundwater pressure underneath the ground surface, it's going to destabilize the type of soil we have here.
The saturated soil here triggered a debris flow that traveled about 1.5 miles before it hit Craigtown. At approximately 25 miles an hour, that would only take about 3.5 minutes. Residents would have had little warning of what was coming. Across the southeast, landslides were one of Hurricane Helene's biggest killers. So what can people do to protect themselves from them?
Watch the National Weather Service warnings, and if there's any wording about landslides, then to not be within one of those debris flow pathways or where the landslides might start. There are online landslide maps available. The North Carolina Geological Survey has put some out so that people can go online and see if they're in one of these areas, and if they are,
Do we
they
have
can
one
go
for
stay
Kerala?
somewhere safe.
Like this? Can we have one? It's a
In
scientific
Valencia, the flatter terrain and more urban environment created a
Anyway, that landslide vulnerability map is very useful. But I forgot to mention that I've not done much work on landslides, but we had 4 papers on landslides for Kunnur, Nilgiris area, debris flows, and using some models and limited data using USLE equation that we came up with. So you are free to refer to those papers. I can find them and make sure that it's available to you. But if you have interest to follow up that kind of work for Kerala, I think that is something interesting. But we did not have all the data that we needed. But if you have that kind of data, the map that what they are talking about for entire North Carolina, we can have one for Kerala. That's the best thing to happen for landslides, vulnerability mapping, using GIS, high resolution elevation models, with geology information, soil types, vegetation, bare soil versus vegetated soil, on top of vegetation or rainfall. If you kind of do that, it's wonderful. It's really service to this state. So I would suggest thinking about that. I will, I think, stop here, although I have in my mind to share one more thing. I don't know whether I have time. Just to quickly on that YouTube video for landslides in Wayanad, I wanted to share my, I mean, I thought you may have seen that too. I will not run the whole 3 minutes, but it's useful to know because I think they're touching the same topic. For those who are from here, you may have seen this before, but those who are from outside, I thought it might be a quick review of the landslide topic that we talked about with Wayanad example. So
Voice is simply faster, more natural, and more flexible than typing. He said he's voice pilled, and I can see why. Whisperflow delivers what Reed calls the future of AI interaction.
the advertisement. This is Wayanad area. Some of you are really familiar who have seen this, but heavy rainfall was the first load. So the extent of the damage you see very clearly. I think as the stream gained momentum, it brought lots of debris downstream. So it even expanded that you saw from another, Planet Lab satellite photo that I showed you before. Um, expanded stream width. Anyway, I think this is kind of a loop right now, so it's more or less done. So I'm going to stop here. But you got the idea, right? I think basically, regardless of the continent, the disasters are striking similarly, almost similar fashion. More rainfall, hill slopes are affected, downstream people are affected. Stream dynamics are more or less the same in terms of bringing down the heavy, flow of water and debris, sediments together. Ultimately, of course, we have to be prepared for this, how to be resilient, how to adapt ourselves, or making sure that the infrastructure is in place to provide early warning systems as well as come up with good predictive tools. Good predictive tools is something that probably we as scientists should be thinking about. And then, the other part, of course, come through later. So science needs to advance in the direction that really makes us face the challenges of hydrologic extremes. So this kind of wraps the holistic view of hydrologic extremes in a way, because we are talking about modeling, we are talking about data sets, we are talking about how to really prepare the communities towards these disasters. I think we have other lectures coming anyway to wrap this up, but I will stop my portion here. But I think we can continue that discussion about um, research part or general talk about how to communicate the research findings. I will talk to Dr. Pramada Madam later about whether or not we can carve out a 30-minute time later. I'm not prepared for today, but if we have time later today, if not tomorrow, we'll see if possible. I'll close my files here, and if you want to come and take over, it'll be great. Thank you.